Well, welcome back, ladies and gentlemen. This will be your pre-calc notes number 2, and I think my smartboard will be working today, even though I cannot maximize the screen. So you do see a sailboat in the background. I won't be able to change that, sorry. But I can use the smartboard, and I'm going to call this pre-calc notes number 2. So on the top left-hand corner, if you can please put that, that would be great, and it'll make us all nice and organized. We have a little bit of a warm-up here before we start the section 1.4 building functions from functions. So if you can please pause this video for just a moment and do the number 1 and 2 warm-up, that would be great. So you can pause right now to do that. Okay, well, you are back, which means that for number 1, when you put -4 in for that x in the f function, you should have got 2. And when you put 2 into the g function here for number 2 and -1 in for the f function and then added those together, you should have gotten 25. Now, number 3, it says, what does finding f of -4 represent? Well, what that means is that when you put or replace -4 in for x, so when you put -4 into the function, you will get a y or f of x value. So really that's just saying that you're substituting -4 into your function for x, and then you will get your output, which is your y value. Down here we're going to talk about sum, difference, products, and quotients of functions, and a lot of this is something you have seen. The sum of two functions, you just add two functions together. Difference, product, and quotient, that is the general form of everything, or theoretical. And down here I am going to show you a concrete example. So let's kind of go right into example number 1. It says let f of x equals x squared and g of x equals square root of x plus 1. So find the formulas for the functions f plus g, f minus g, f times g, and f divided by g, and lastly g times g. And then you want to give the domain of each. I don't want to diminish what it does say up here about the domain, because that, if anything, is going to be something we need to address. And as we move through example 1, we'll talk about that. But let's start with just adding f plus g together. Well, f of x is x squared, and g of x is square root of x plus 1, so we take your f of x and add your g of x together. And then you would typically simplify it, but there's nothing here to simplify, so this is it. Now the domain here, if you look, you obviously cannot have a negative under the radical, so that means that your domain has to be equal to 1, or excuse me, equal to -1 or greater. So you can actually put -1 in. -1 plus 1 is 0, and that would give you 0 under that radical. And of course square root of 0 is 0, but if you go any smaller than -1, that's going to be where your issue is. So the restriction is you cannot have negative under the radical, and so that implies the domain is going to be from -1 all the way up to infinity. Now if we continue this, we subtract the two functions. Again, take your f of x function, which is x squared, minus your g of x function, which is x plus 1. And nothing to simplify, so in that respect it's not very interesting. Now let's look at the domain. Again, notice it's the same domain because you cannot have a negative under that radical, and the only thing that would cause that is a value smaller than -1. So we're going to do that again. Now f times g is going to be where you take your f of x function, which is x squared, and you're going to multiply it to your g of x function, which is the square root of x plus 1. And again, not able to simplify it. This is really it. You could, I suppose, scrunch it together without a multiplication symbol, but that's that. Now again, not to be redundant, but you're noticing hopefully a trend here where we have a domain like the others. Now letter D, now I don't, they do get very exciting here, so just kind of hold tight. F of x divided by g of x, you have your f of x divided by your g of x. And this domain is a little different because, one, you have a restriction because of the square root, and the second restriction is that you cannot have a 0 in the denominator. So, all of a sudden I'm just looking at this. So when we talk about this, we want to make sure that we have not a 0 in the denominator, and we want to make sure it stays positive. So if you think about this, again, -1 would, that's as close as you can get as far as under the radical, but you know what? If you put -1 under there, -1 plus 1 is going to be 0, square root of 0 is 0, and that is a problem in the denominator this time. So here's the interesting thing. You can go all the way down to -1, but not actually equaling -1 this time. So this one, you have to be careful with that restriction. So again, you can go all the way down to -1, but not actually equaling -1, because that would cause a 0 in the denominator, which would cause that function to be undefined. G times g, well, this is kind of an interesting one as well, and I'm kind of getting all misaligned here. But you have the square root of x plus 1 times the square root of x plus 1, so just to make it easier, I'm just going to do this right here. And you know what, you could leave it that way, but here's the thing. Square root, when you have a square root, square, we know those undo each other, so we end up, ooh, geez, that was weird. We end up with x plus 1. When you simplify that, I don't know what that other thing is, but anyway. So x plus 1, so when you have a function equaling x plus 1, that's a line, but keep in mind, now let me take a step back. A line has no restriction. So, especially this kind, because it has a slope of 1, so it would be -infinity to positive infinity. But you need to remember that the original functions have restrictions. So if you look up here, this original function, no restriction, but this one did have a restriction where you needed to have values that are positive under the radical, otherwise you have imaginary numbers. So even though on the surface this one looks like it doesn't have any restrictions, you need to remember that it is a product of two functions with restrictions. So the domain would be -1 all the way to infinity to meet this restriction up here for that g of x. So that's where I'm saying you can leave it as that square root of x plus 1 quantity squared. I'd rather you put it as x plus 1 and recognize the fact that the domain has restrictions because of the original functions. Okay, so let's kind of come down here by example number 2 and see what we have there. It says, using the functions from example 1, find f of g, excuse me, not f of, f times g, the product of f times g, given that x is 3. So what this is saying is that you can take this function right here that we created, this one right here, and put 3 in there for x, and that would be your value. So 3 squared is going to give you 9. I'm just going to write this down here so I remember, times the square root of, if I put 3 in for x, I have 3 plus 1 is 4. So again, all I'm doing is evaluating that letter C's function in terms of 3. So I have 9 times 2, which is 18. Now, the fascinating thing about this, I don't know if you'll find it fascinating, I do, is that if you put 3 in for f, and then 3 in for g, and then take those two values and multiply them together, you get 18. So the point of really what we're doing, or how you use this, this whole example 1 and 2 thing, is that you're creating these new formulas that make it faster. I guess that's the way of thinking about it. I don't know how well I'm convincing you, but let me show you in letter B here. G times g, and then given that you're putting 8 in for x. So here's the thing. You could have put 8 in for g, and then 8 in for g, and then multiplied it together, and that's your value. Or you can take this one that we found right here, which was this right here, and put 8 right in for x really quick, and you know what? We get 9. Whoop. And again, that is exactly what you would get if you evaluated each function separately and then multiplied it together. So that is really kind of a intro to functions and doing different operations on them. Now we're kind of getting into the, I don't know, sometimes people find this a little bit more complicated, but these are compositions of functions. I know you saw this in advanced algebra last year. What you may not have seen is both notations for composites, and that's this right here. So both of these can be used interchangeably, but they both mean f of g of x. So you're taking your g of x function and putting it into the f of x function. So a definition of a composition of function is that you're really literally taking one function and throwing it into the other and creating a whole new function with a whole new values for x and the domain. So if you read that definition, it says exactly what I'm kind of trying to sputter out, but much more eloquently than what I'm doing right now to it. But you notice here it says figure 1.55 in the composition. I'm right here. In the composition of f of g, the function g is applied first and then f. This is the reverse order in which we read symbols. So we're usually reading left to right. I'm just letting you know that with compositions, we really actually take the g of x function and put it in for f. Again, I'm not sure why that did that. So sorry about that. Let's try that again. So you're taking the g of x and putting it into the f of x. If you're not really quite sure what I'm talking about, let me just show you by a demo. I find that to be a little bit easier. So this example number 3, it says let f of x equal x squared minus 1, and then let g of x equals the square root of x. Find the domains of the composition functions. So what's going to happen here is you're going to take your f of x function and put it into your g of x function. Well, how I do it is I look at my g of x function, which is the square root of x, but instead of x, wherever there's an x, I'm now going to put f of x, which is x squared minus 1. So again, when you're dealing with composition, you're throwing your one function into the other, and you're reading it from right to left, exactly opposite of what you're used to doing. So this square root of the quantity x squared minus 1 is the composition of those two functions, g f of x. The domain? Well, here's the thing. We know that we can't have a negative under the radical, so we know that x squared minus 1 has to be greater than equal to 0. So because of that, you can really, actually solve this inequality out if it helps you out. But really, and let's just do that just for fun. So x squared is greater than equal to 0. Remember the good old days where you separate it, you have x, when you take the square root of both sides, you have x is less than, not x is greater than 0. I'm so sorry. That should have been a 1. I should have added 1 to both sides. You know what? Let me try that over. Oh, I could do better. So x squared, I add 1 to both sides, so it's x squared is greater than or equal to 1. Then when you square root both sides of the inequality, you do need to think about your two solutions. One's going to be x is less than or equal to negative 1. The other solution is going to be x is greater than or equal to 1. So that is a nice review of your Algebra 1. And it applies here for domain. So what this is saying is, you know what? Your domain makes sense from negative infinity all the way to negative 1, because it's equal to, union, we're going to jump to 1, because it has to be greater than and equal to 1, all the way up to positive infinity. If you want, you could graph this, but I am going to let you know that it's not as simple as just graphing the square root function of the composite. You actually have to consider both of them. So on the graphing calculator, it's a little tricky, and I will show you that in class. Now let's do letter B here, where it says let's take this g of x and now put it into the f of x instead. So my f is x squared minus 1. So wherever there's an x, I'm going to substitute my square root of x. So I'm going to take this and throw it into wherever there's an x. That's how you create a composite. So I'm going to have square root of x, that quantity squared, minus 1. Now, this is fine, again, to leave it this way. Really, for simplifying, you can say that it's x minus 1, because of course we know square and square root undo each other. But remember that while a y equals x minus 1, this x minus 1 is a line with no restrictions, the original functions did have a restriction. Especially well, not just especially, the only one would be this one here, right here, where you need to make sure that its x is greater than or equal to 0, otherwise you have an imaginary number instead of a real number. So the domain for letter B, which I'm going to say is this function here, but again you could put either one, is going to be starting at 0 and equaling and going to positive infinity. Okay, so that is a rehash of composites, and I know again you've seen these before, but I did want to kind of remind you we're using square roots a lot, which makes it a little more complicated, messing around with the domain, and then of course looking at that different notation. So while it might be a review for many of you, I'm sure you have learned something new, hopefully. Example number 4, modeling. This is a great example of how or why we even do compositions. In the medical procedure known as angioplasty, doctors insert a catheter into a heart vein through a large peripheral vein. That sounds horrible, but it happens every day, and it's really interesting to watch if you ever have a chance. Well, what they do is they inflate a small spherical balloon on the tip of a catheter. Suppose the balloon is inflated at a constant rate of 44 cubic millimeters per second, and it does say see figure 1.58. I don't have room on here, this note guide, but I do want to say that that figure is in the textbook if you wanted to look at that. I also want to say if you need a little bit more clarity with this problem, because it is kind of a dense problem, it is in the textbook as well. But let's kind of take a step back. It says find the volume after t seconds. Well, you know what? The volume is going to be 44 cubic millimeters per second. So 44t is going to be your volume in terms of time. Now, with that said, I want to kind of remind you something. The volume is of a sphere. Back in your geometry days, don't know if you remember it, I should make you look it up, but for the sake of time here, volume is 4/3 pi r cubed. I'm sure you're like, oh yeah, I remember that. Now, why is that important? Well, because what the spherical balloon that they're putting in the catheter, or on the tip of the catheter, is a sphere shape. And in letter B, it's going to ask when the volume is V, what is the radius R? That's a fancy way of saying, you know what? You have that sphere volume formula, solve it for R. So you're solving for R on that sphere formula. And that is kind of interesting because we've got a fraction and all that. The first thing I'm going to say is I would multiply both sides by 3 to get rid of that fraction. So you have 3v equals 4 pi r cubed. Then I divide out by 4 pi. So you have r cubed equals 3v divided by 4 pi. And then you know what? You cube root both sides. So you end up with r equals the cubed root of 3v over 4 pi, where again v is volume, pi is the number pi, and r is radius. So that is what they're asking for in letter B. So there's no way I was going to be able to fit it there, so I'm just letting you know that this right here is letter B in a nutshell. Letter C, it says write an equation that gives the radius r as a function of time. Oh, there's the composite that we were talking about. So it says write an equation that gives the radius r as a function of time. So notice that the equation that we have in letter B is in terms of volume and radius, but not in terms of time. So what we want to do is replace that volume, get rid of it, because we want the radius, but we don't want the volume, and instead of volume, we're going to write it in terms of time, which is why we did that little thing in letter A. Now, I'm going to do this part up here, trying to keep you from getting confused, though, and I'm going to have the cubed root of 3, but instead of saying V, I'm going to say that is times 44t. Where am I getting that from? Right up here. So instead of volume, I'm replacing that with that 44t because we know that it's 44 cubic millimeters per second. And whoop, I have to close that up, divided by 4 pi. Now you can simplify this, and by the way, I should probably say this is equal to r. So of course you can multiply the 3 times the 44 and go there. I'm just going to leave this just like that because of my space, which is really naughty because it really should be simplified. But I need to answer this question, what is the radius after 5 seconds? So we have this composite function that we just created in letter C with radius in terms of time, as a function of time, excuse me. And now what's awesome is that I can take that 5 seconds and just put in for time and get my radius. So if I put 5, and I'm going to change colors here. So if I take this 5 seconds and put it right in here in time and solve for r, that is the radius that this procedure would need to have in order to accommodate all the restrictions. So let me just do this here. So I'm just saying the radius is going to be the cubed root of 3 times 44 times 5 divided by 4 pi. So we have all these numbers. So 3 times 44 times 5 divided by 4 pi. Take the cubed root of that, and your radius should be approximately 3.74 millimeters. I like this problem. This is a good problem, a good example of compositions. Because again, you've seen compositions before. This is a good example of why we use them. You see it a lot in investments and that kind of thing, and economics. But this I like this one for the in physics. Physics use compositions all the time. Anyway, the homework is at the bottom. I am going to say that I'm going to edit the homework, so don't do number 10. And instead of doing 15 through 20, ooh, crap. Oh, I did it again. Hold on a minute. Sorry, you guys. Don't know why. Don't want to ask why. So instead of doing this, I want you to do 15 through 18. And oh, for goodness sakes, you can obviously see I'm having some functional difficulties. Maybe I should just stop while I'm ahead. Okay, get rid of 10, and then don't do number 19. Let's do it that way. Okay? Well, thank you for tuning in, and you will have a chance to ask me questions on any of this when we see each other next. Take care.